Don't scrap your moldboard plow. I'll be talking about the connections between what's going on in Lake Erie and what's happening on cropland in northwestern Ohio. As we see it from studying rivers that are kind of the connection between the farmland and Lake Erie. Lake Erie has undergone what's called reunification. And so if we look at a long-term record of Lake Erie going back to the 1970s through 2020, and look at various eutrophication indicators such as harmful algal blooms, oxygen depletion in the Central Basin, shoreline falling by algae, or just algal densities. All of these would show that in the 1970s things were really bad. They improved a great deal, now have gotten worse again to the point where they're worse than they were in the 1970s in many instances. This is a generalized curve. If we look at a specific example, this might be algal densities, we can see that they dropped into the mid-1990s, then have gotten worse again, both in the Western Basin and the Central Basin. So this whole issue of reunification is thought to be caused by the amount of phosphorus that's going into Lake Erie down the rivers, the major tributaries such as the Maumee. So if we look at Lake Erie as a whole and look at the total amount of phosphorus going into the lake back to the 1967, this 25,000 metric tons dropped very rapidly to the early 1980s, and then has dropped rather slowly since that time. That's total phosphorus loading into Lake Erie. This drop here was really caused primarily by treatment being implemented at municipal sewage treatment plants. That was the major source that really caused the big drops in loading. But total phosphorus hasn't increased since the early 1980s. It's decreased slightly. So why are we calling for 40% reductions in phosphorus loading to Lake Erie if total phosphorus hasn't gone up? Well, the reason is that what has changed is not the amount of phosphorus, but the composition of total phosphorus going into the lake. Well, what do I mean by composition? This is the Sandusky River in Tiffin during a runoff event, rather brown, muddy water coming down. We can pull a sample, and we have 20,000 samples from the Sandusky River near Fremont at this point in time. We can analyze it for total phosphorus that includes both the phosphorus that's dissolved in the water and the phosphorus that's attached to the sediment. And then we can filter out what's attached to the sediment and simply look at the clear water that comes through. That's what contains the dissolved reactive phosphorus, or DRP. The particulate phosphorus, we actually don't measure it directly, but we do measure total phosphorus, and we measure dissolved phosphorus, so it's easy enough to calculate by difference the particulate phosphorus that's going down the lake. And what's important to know is that just like on your cropland in the soil, not all of the phosphorus present in the soil is available to support crop growth. Maybe only half of it is, if that. The same for phosphorus going down into the lake. The particulate phosphorus is only about 25% bioavailable. The dissolved reactive phosphorus is 100% bioavailable to algae. So let's look at the trends in these two kinds of phosphorus in the Maumee River. This goes back to 1975 for loading, and this is the particulate phosphorus loads. They're larger than the dissolved phosphorus, but they have been dropping slowly. They're very noisy from year to year because of the weather conditions, for that matter. That's what in any one year, the loading is driven by the amount or the weather conditions that year. But if we look at the total or dissolved phosphorus loads, they dropped, and then they've gotten much, much larger again. And although it's still variable from year to year, likewise, the algal blooms in the lake vary from year to year. But what we're really concerned about then is this increase in dissolved phosphorus loading going down the Maumee River and the other tributaries going into the lake. So why have the particular phosphorus loads decreased while DRP loads have increased? That's what has happened. The net effect of these two is that the amount of phosphorus that's bioavailable to stimulate algal growth has increased. So that's the net effect on bioavailable phosphorus loading. So why have these things changed? If we look, well, the phosphorus load in any one year depends on the product of phosphorus concentrations in the water times the river flow. If river flow stays the same, then the loading will depend on the concentrations. Concentrations go up, loads go up. Concentrations drop, loads drop. If, on the other hand, if the concentration is the same, but the river flow goes up, the loads go up. It's just a product of the two all the time. And so which has been more important in causing the changes in loads? Is it because we have more water going down the river or because concentrations have changed? These are the concentrations of particular phosphorus up here in the Maumee River. They've generally gone down. Here's the concentrations of dissolved phosphorus. They dropped rapidly up to the mid-1995, and since then they've tended to go up by quite a bit. And this is the loads of, the flow or discharge of the river, and it too has gone up somewhat. It's certainly variable from year to year and more variable than the concentrations, but the increase in concentration of dissolved phosphorus is much larger, in fact, than the increase in discharge of the river. So we think it's so the question becomes, what's happened on the cropland? Well, how do we know it's cropland? Let's back up a notch and look at cropland issues. How do we know agriculture is causing these changes? Well, this is where we've all heard of the watershed approach, and that's what's used in order to quantify non-point pollution or land runoff from point sources. This watershed approach then, this is the boundary, any rain that falls inside that boundary runs downhill to these streams. These pipes here are an example of what would be coming in at the municipalities in the watershed. And so the way you measure the non-point source pollution is to get information on how many tons per year of phosphorus are coming in from all these treatment plants. And that's reported to the U.S. or Ohio EPA. And then you also measure the total watershed output. And given those two measurements, the total output from the watershed, and that's where our lab comes in. We're monitoring total watershed output at 18 stations in Ohio now, with 3 samples a day going year round. And when there's a flood runoff, we analyze all 3 of them, otherwise a sample a day. So this is an extremely detailed data set for runoff. In any case, what we do then is simply take the total watershed output, we subtract the point source inputs, and that gives us the non-point source TP output. And so when we do that for the Maumee River, for the last 10 years, this is what we get. The blue bars here are the point source inputs, on average about 5%, only 5% of the phosphorus that goes out the Maumee River. That's at most what's coming from the point sources like Fort Wayne and Defiance and Lima and so forth. So anyway, non-point source variable, 95% of the problem. About 73% of the land use in the Maumee is agricultural land. And so that's just looking at the land use, you have to conclude that most of this phosphorus is coming from cropland. Okay, so how have changes in cropland management changed these loads or concentrations? Well, this is a success story, believe it or not. It does reflect the success of the erosion control programs that farmers have implemented on the cropland in northwestern Ohio. We have seen decreases in the concentrations of sediment in these rivers. Sediment has decreased even more than the particulate phosphorus because the sediment control programs, erosion control programs, reduce the larger particle size more effectively than they do the finer particle sizes, and the fines are what have a higher ratio of particulate phosphorus. So if we were to plot sediment up here, you'd see even bigger reductions than you see for particulate phosphorus. So these, the erosion control programs have worked. Now, what about the causes of the increased DRP? Well, I'm saying that the increases in DRP concentrations are caused in part by these same erosion control measures. So the erosion control measures that stop particulate phosphorus end up increasing DRP concentrations for reasons that are well known and were known in the 1970s when we launched the erosion control programs. But the particulate phosphorus back then was better than 80% of the total phosphorus going down the river was particulate. And that left less than 20% being DRP. So it made sense in order to achieve total phosphorus reductions at that time to focus on erosion control. But now the dissolved phosphorus is more than 30% of the total phosphorus load, and it's bioavailable. So let's see just how this happens. How is it that no-till can increase the DRP concentrations? And what we simply look at is how phosphorus moves from cropland to streams and rivers. This is a diagram from the 1970s. Rainfall starts to run off the field when it exceeds the infiltration capacity of the soil. And this will erode the surface materials that carries the particulate phosphorus. But also this rainfall that's running off the surface interacts with the upper layer of soil in the field. This is called the zone of interaction. And so it's this interaction that will move some of the phosphorus that's present in this zone of interaction as soluble phosphorus into the runoff water. And so the surface runoff carries both particulate and dissolved into the rivers. A small amount of phosphorus was thought to be leaching and coming under subsurface runoff. But what we also know now is that the DRP concentration in this runoff water, the concentration of dissolved phosphorus, depends on the soil test levels in the upper inch of soil, or the upper 2 inches of soil. And so the higher the soil test levels, the higher the concentration in the runoff water. We also now know that a whole lot of the phosphorus that's coming into our streams is actually going through macropores down to the tile drainage line, and some of the recent research has shown that the bulk of the dissolved phosphorus and even a large share of the particulate phosphorus is moving through these macropores down to the tile lines and coming out the tile. And it used to be we thought only the nitrate came out the tile. Now we recognize that it's not just the nitrate, that there's a lot of dissolved phosphorus coming out thanks to macropores, it turns out. And as you may know, no-till, mulch-till, these things can increase both superficial phosphorus, soil test levels, and macropore development in the soils. So there are two ways that no-till, mulch-till, these erosion control measures can in fact increase DRP runoff. So in the Sandusky watershed, we launched a stratified soil testing program. And incidentally, the phosphorus is fairly immobile in the soil, and so when you apply phosphorus at the surface of the soil, or when crop residue breaks down at the surface, that phosphorus hangs around the surface and it builds up the soil test level. This is called phosphorus stratification. It happens in forests, it happens in pastures, it happens all over, as it turns out. So we wanted to see how much stratification was present We collaborated with CCAs. We tested over 1,800 fields. We had the CCAs collect an agronomic soil test, 0 to 8 inches. But at the same time, they collected cores that they divided into 0 to 2 and 2 to 8. Also 0 to 1, 1 to 2, 2 to 5, 5 to 8. So we have a fairly large data set. These are the averages that we got. The average soil test level, this is Mehlich, it's not pounds per acre, this is the Mehlich test in part per million. In the Sandusky is 45. The average Mehlich at the top inch was 69 part per million. The average Mehlich down at the bottom, the bottom 3 inches, was 35 parts per million. Now those are low phosphorus test levels, relatively low Mehlich. Yet the Sandusky River, where we collected these, has almost the highest export rate of phosphorus and dissolved phosphorus and total phosphorus of any of the rivers we study, except when we get to the Scioto and the Great Miami, where we have big cities that are still dumping in excessive amounts of phosphorus. The phosphorus removal requirements hit the Lake Erie Basin cities, but not the Ohio River cities, at least initially. So anyway, what do? Well, this is another picture of the same data. This shows the agronomic soil tests on the x-axis, soil tests at the upper inch on this axis. If they were the same or 1 to 1, they'd be along this red line right here, the heavy red line. And you can see that the amount of stratification at a given agronomic soil test level is highly variable. And so what else is new about variability in soil testing, for that matter? In any event, it is highly variable, and so unless you measure it, you won't know what your what fraction of your total phosphorus content in your 0 to 8 is actually way up at the top inch, that can dry out and not serve as a particularly good source of phosphorus for your crops in a dry year. So we're advocates of this kind of stratified soil testing to figure out, so you know where your nutrients are. And on average, the superficial soil test levels are 55% higher than the agronomic soil tests that you would be looking at when you get a soil test. Do increases in Mehlich 3 soil test levels in this range and of this amount really matter when it comes to dissolved phosphorus runoff? Well, this has been a controversial point in Ohio, but there's a lot of data that shows that yes, even at these low Mehlich test levels, under 80 and so forth, there is an increase in dissolved phosphorus with those kind of increases in Mehlich. And this is comparing 3 different soil tests. This is a widely used thing. But so in any event, what we do see is that Mehlich increases in this range do increase dissolved reactive phosphorus. And here's an example of where you started no-tilling, conventional tillage. This is what happens to the DRP runoff at a edge of field level. And there's quite a bit of data of this type. That's an example. So another cause of increased DRP concentrations, remember I said that soil test levels were in part of the cause, is what we've been talking about here often today is fertilizer application just before precipitation. There's lots of edge of field data on that, but we can also see it in the rivers. This is the Honey Creek discharge fall of 2011. It's a tributary to the Sandusky River, about 130 square mile watershed. So it's a pretty good sized watershed. And that fall, we had this is dissolved reactive phosphorus. And when we get up to a 400 or 0.4 milligrams per liter of dissolved phosphorus, that's unusually high. Well, the next thing we knew, we were getting samples around 0.6 milligrams per liter. And then a storm where we had dissolved phosphorus at 1 milligram per liter in a river draining 140 square mile watershed. This was during our soil stratification meetings or study, and what we found out was that the custom applicators were in the fields. It was a wet fall, but they got to get the fertilizer out. So they did go out, and then you had rainstorms. Here was an example of a rainstorm right after custom application, another one. And so we had, fortunately this is unusual, but it does happen, and you can pick it up in the river monitoring programs. This is from a smaller watershed we have up in Defiance County, unnamed tributary to Lost Creek, so it's pretty small. But in any event, we had this picture of application on snow, and then shortly after we saw that picture, we had some snowmelt events that, again, we had our GRP skyrocketing up to exceptionally high values. So we can see it's not just at the edge of field levels that these things happen, but when you're in an agricultural watershed, you see it at the watershed scale as well. Well, so the problem is you people are amazingly efficient in the use of the fertilizer that you're applying. What do I mean by when I say that? Well, we can calculate the pounds per acre per year of total phosphorus and dissolved reactive phosphorus that are coming out of these watersheds. And so, for example, the Maumee is 0.29 pounds per acre per year of dissolved phosphorus. And then we can do some adjustments, recognizing that some of the land use, like forests in the watershed, maybe 10%, don't export at that high a rate. So we can adjust this up to maybe from 0.29 to a third of a pound per acre per year. And that dissolved phosphorus, then, here we're comparing this with the maintenance application, and NRCS said in the Sandusky watershed, over the rotations we have, maintenance application would be about 47.5 pounds P2O5 per acre per year. That translates into 20.8 pounds of phosphorus per acre, 1.6%. So, in other words, what's causing the problems in Lake Erie in terms of dissolved phosphorus represents only 1.6% of a maintenance application to sustain the yields that we have in this area. Is that a problem? Yes. How in the world are we going to reduce it any further? Well, there are things you can do. But I think it's important that everyone recognize what the situation is and that farmers are, in fact, not losing excessive amounts. Now, a couple things, though. How about the bad actor? You know, how much of the problem can be blamed on just these isolated people where we have, really, really, really bad situations? And the general thought, I think, is that we can't blame very much of it on them. In fact, it's all of us doing a little bit that is the problem. And so what can we do? And so that's where, how do we reduce this loss rate of less than 2% by 40%? Well, that's what a lot of the efforts in the conference today are working on this issue. But what we would say is that you need to do or include stratified soil sampling in your monitoring your fields that can help you agronomically. Where fields are highly stratified, i.e., it turns out, I'm going to skip, 4R methods to minimize subsequent stratification, avoid application on frozen and snow-covered grounds, that's already in the works. Use water management practices that minimize total runoff. If we can keep more water in our soil, then that's going to reduce the total flow volume going down into the lake. Build soil health to improve soil tilth, and include rainfall infiltration. The soil, the subsoil that we have long before you get to where the tiles are, is a treatment system if we can get the water to move through it rather than down the macropores. But what might we accomplish if we had stratified soil testing data? For example, if we would take the fields where we have superficial soil tests at 20 part per million higher than the agronomic. So we'd be able to pick out the fields with at least that much stratification, 20 part per million, and do a one-time soil inversion, say before corn in a 3-year rotation. So in 3 years, well, let's say it covers about 50% of the fields have stratification greater than 20 part per million. So 50% of the fields we would treat, and you would treat that over a 3-year period, plowing perhaps before corn each time. That's not going to change your erosion rate very much. I should have also mentioned that where stratification is studied in a pure no-till system, stratification is much higher than what I've shown you. This is a small amount of stratification, but we have rotational no-till, not pure no-till. And another problem is that even when you use cover crops, that can increase stratification. Anyway, the calculations are that this treating half the fields with a one-time soil inversion would reduce the dissolved phosphorus loading by 28% by the end of that 3-year period, assuming that you're taking steps to minimize stratification subsequently to the plowing. That means the no-till and the cover crops and things like that. But from the preceding talk, you know that to achieve a 28% reduction by drawdown will take a heck of a long time. And so this could be, to the extent that any kind of quick fix is available, this at least ought to be investigated at this point in time to see if it would really work, given the soil types that we have in northwestern Ohio.